All right, so welcome everybody. I can't tell you how happy we are to all, well, how happy I am to have you all at the table. Let me introduce our fellows here. Dr. Mats Larsson is a professor of molecular physics at Stockholm University, and he's on the Nobel Prize Committee in physics. Over here is Neil Hickey. Neil, well, tell us a little bit about you.
Well, I'm a lifelong ink-stained wretch, a journalist, with various newspapers and magazines. And in my old age, I have come to rest at the Columbia Graduate Journalism School here in New York. And I'm very happy to be here to meet you today.
And Elizabeth, who the heck are you?
I'm someone who's been extremely obsessed with extreme action my whole life. And I've been on the quest for what is a real move, and in the process of doing that, with 50 tons of equipment and a lot of invention and experiment. We do an extreme action show called Forces, and we tour the world in theaters, trying to do the impossible and break the speed of sound, and perhaps travel faster than light.
Oh my.
And get hurt doing it too, I might add.
Oh.
So Elizabeth makes movement. I cover movements. I'm an independent journalist. My show these days is called GRITtv, Grassroots Interactive Television. And together with HD Fairfield, we're very excited to be hosting this conversation. So it was just last year, in the summer, that we got big news, covered all over the world by good journalists. They tried to help us understand it, but I bet I'm not the only one that didn't quite grasp it. What is a Higgs boson?
In the so-called standard model, you have a certain amount of particles. You have leptons and you have bosons. You have the quarks, the bosons, the quarks, and you have the electron, the muon, and so on. And they are forming families. And you have the neutrinos. These are very light particles that penetrates everywhere. But in order to understand how they can gain mass, in the standard model there has been one particle that was proposed already 50 years ago. One of the proposers was Peter Higgs. That in order for the other particles to gain mass, you needed them to interact with this so-called Higgs boson. And since then, of course, a quest has been to try to find this particle.
I still suspect there are some people out there who don't actually know what's colliding in the collider. It's a great big track, right?
You take a beam of protons. A proton is just a hydrogen atom when you have removed the electron. Then you have a proton. But then each particle also has an antiparticle. And then you can collide protons and antiprotons, for example. In order to see the particles that are heavy, you have to go to high collision energies. Because if you're too low in energy, you don't create these particles. There is a relation between energy and mass that Einstein discovered. And this is the sort of the bottleneck. If you're at too low energy, you will never see any. In order to keep the particles in orbit, you have magnetic fields. And the higher energy, the higher the energy, the higher the field strength of the magnets. And that's what they have to do now. They have to push the magnets to higher field strength.
Where does the Higgs boson research end, if in fact it does? What are we looking for?
Well, the hope was that one would find much more at CERN, at LHC, than just the Higgs particle. Really what you want to see is to find a departure from the standard model. Because it's generally conceived that that could not be sort of the final answer, the final theory framework.
When you talk about the standard model, what do you mean, and why do we need a departure from it?
What you want is to combine the forces. We know there are four forces. There is the gravitation, there is the strong force, the weak force, and the electromagnetic force. And right now it's very difficult to combine gravitation with the three others.
Why?
Because the structure of the theories is different. I mean, the gravitational theory is the was developed by Einstein. It's the general theory of relativity, and that's a theory on the grand scale, whereas the quantum mechanics describes the microscopic, where you have the electromagnetic weak and strong force. So string theory, for example, is an attempt to combine gravitation with the other forces.
Are we any closer to finding that grand unified theory than we were 10 or 15 years ago?
Probably not. I don't think
Will
so.
we ever find it?
Nobody can answer this. I think the question now is whether, of course, as you said, it has been the Holy Grail, and sort of just the beauty of having a single theory that sort of can describe all the different interactions. You can certainly find people who would be a bit pessimistic now.
So given all the things you could do with your time, why that? Why is that? I'm getting it. Why is it so important?
Well, what was interesting, of course, was that LHC is probably the most complex, or at least one of the most complex constructions ever done by human beings. I mean, it's an extremely complex machine.
The Super Collider.
The Super Collider, yes. Actually, the name is the Large Hadron Collider, yeah.
We had a conversation around this table recently where a young man was holding forth about the amazing new discoveries of current science. And a classicist at the table, a professor at NYU, said, "A little humility, young man. What makes you think that the scientists of today are genetically or dispositionally smarter than was Ptolemy or the scientists and mathematicians of the ancient world, whose theories held for hundreds of years before they were proven to be completely untrue?
No,
why do we think we're right?"
Why not?
What would you say to her?
Well, I mean, it's certainly correct that I don't think we are smarter now than 100 or 200 or 3. I mean, just look at Newton, for example, or Leibniz. But of course, science is a sort of an accumulative process. I mean, you accumulate more and more knowledge, and so you build a solid foundation. But of course, then there are all the time new challenges to understand more and more complex systems. And there are certainly, I mean, just look at the human being. I mean, of course, we have the whole DNA sequence, but there are many questions that are not answered by just knowing the DNA sequence.
Do you ever get any help from artists?
I would say that scientists are usually quite often interested in art or music and so on. I mean, because at least I think it's a different part of the brain that works. I would never allow my brain to analyze why, for example, I like certain Mozart operas or something like that. I don't want my analytical part is banned from that.
And you, why are you interested in science, Mr. Artist?
Well, I guess I have the absurd quest of understanding, like, what is a real move, like, rather than stringing decorative or Baroque movement together the way ballet did and does. I wanted to know, is there such a thing as a real move, that you couldn't reduce it to any subsets? There is a real move. So my journey has been about essentialist acts on a certain level. But I wanted to know, for instance, why can we memorize melodies and less so pathways in space? Like when you go to a dance concert and they're moving around in these fairly complex floor patterns, people either perceptually don't have a nomenclature for that, and so therefore it doesn't go into the brain in the same ways when you hear equally abstract movement and sound. I just always wondered why people memorize melodies and not pathways, spatial pathways.
So that's a scientific investigation, you think?
Probably not. I mean, but I still think there's a problem with our field, which is movement, because there's less content in understanding the syntax and the grammar of these fundamental principles. space and time.
Well, movement is movement and gravity are all of a piece, are they not? I mean, obviously our solar system depends upon the movement of those planets around around our silly little star, which is an insignificant one and perhaps an insignificant galaxy.
Well, could I swing just back for a second about you saying that the solar system moves, but they move in an honest way. Dancers camouflage the effect of gravity, so they fake their moves and fake their timing. So it's all artificial. And so my point is that I want to move in a true way, and that would need to deal with not camouflaging gravity. And if you're falling, you fall and you smack into the ground and abruptly stop. So what would that system be? And that's part of an investigation that I think movement as an art form critically needs.
Talk to people today, Mats, who are looking at our various crises, economic, climate, social relations, war, and wondering how do we justify spending the kind of resources that we still do in science. What are your hopes for the sort of the visible future that we might find? Do you think, for example, we'll find a new energy source or find our way out of our energy
Yeah, we have to,
crisis?
and I think that there is a lot of good science going into this now. Certainly here in the US, I mean, several of the national laboratories, they're going to put a lot of effort into finding new energy sources or making known energy sources cheaper. Absolutely. But at this point, I think you have to have a broad approach, and it's difficult to say exactly what's going to... Solar energy is probably going to be cheaper in the future, I would think. But I think you also have to have a different approach to your cars. I mean, they are quite big and consumes a lot of gas.
The question is perhaps a little out of your discipline, but there's some serious science going on in the U.S. about what we call SETI, S-E-T-I, the search for extraterrestrial intelligence. I don't for a moment believe in flying saucers, but in any case, we have been discovering recently what are called exoplanets. That are planets that are around stars that are stable enough and old enough, and perhaps the temperature and the barometric pressure is possible. It makes possible the generation of some form of life, some basic forms of life. In the hundreds of billions of stars out there, which some of which we now know support planetary systems that conceivably could support some form of life. What are the chances of intelligent life? And it's a serious question.
I think it's absolutely sure that there must be life. Yes. I mean, there is no way that, I mean, as you said, I mean, now they have discovered hundreds of planets. Yes. And they start to discover, in the beginning it was the giant planets like Jupiter, but now they start to discover planets that are in the so-called habitable zone where life could exist. And this has happened only over 15 years or so. One very important question that I think is fascinating to think about is, and we just touched upon it, what is the origin of life? I mean, how did life start on Earth? Nowadays we know, and this is research I've done myself, that there are fairly complex molecules in what's called the interstellar medium, which is really the medium between stars. There are molecules of equal complexity as amino acids, for example. And there has been some disputes whether one has seen an amino acid or not at this point, but I'm quite sure that sooner or later there will be discoveries of amino acids. And this means that there are complex organic molecules in the stellar medium, and also available where new planets are formed. So one can easily see that organic molecules could have been transferred to the Earth when it was a very young planet, and then slowly life started to evolve. But of course we don't know very much about this yet. It's still speculative, but there is a new branch of science called astrobiology, and this is certainly not only a physics problem, it's a cross-disciplinary, all the way from biology to astronomy.
So once we figured out how it started, then we get into why did it start, and I think we should probably call it a day.